Good afternoon, everyone, and thank you very much for bearing with us these last couple of minutes while we're just setting up here. We've got a really exciting ECA Learning Zone webinar for you today. You've got on your screen now our two wonderful presenters. We've got Darren Crannis, Technical Manager from the ECA, as many of you will know, and Spencer Henry from ElectricalOM, ECA Commercial Associate and trusted partner throughout the years, who many of you will have met at the various ECA roadshows that we've put on over the years. I won't spend too long making introductions. I'll shortly hand over to Darren, but I'd just like to say that this session is being recorded and will be available on our YouTube channel and members area of the website, probably from tomorrow morning once the session is concluded. And we're doing things a little bit differently today. There aren't slides as such. We want this to be a bit more of an interactive session for our audience and our ECA members. Darren will give a brief overview, and then Spencer will share his screen to give you a live demo of the ElectricalOM software. And with that said, we're also going to be taking questions throughout the session, not just at the end. So do send us your questions as and when they come to you. And every now and again, we'll do a quick pause, pick up any questions and move on. So I'll stop there. Over to you, Darren, to kick off the session.
And thank you, Omar. So hopefully, yeah, thumbs are up, the microphone's working. Slight bit of microphone trouble today, but hopefully we'll get through this. My name's Darren Crannis. I'm a technical manager here at the ECA. And I've sort of been electrical contracting sort of 10, 12 years before I came over to the ECA a couple of years ago. And I've got a background in sort of mostly power, telecoms and design. It's delighted today to be joined with Spencer. So I'm going to quickly hand over to Spencer for a couple of minutes so he can introduce himself, because some of you on the call may know him well, others may not. So I think it's only fair that I introduce Spencer. So Spencer.
Hello. Yep. So I'm Spencer. I'm an electrical consultant. So I do various electrical consultancy around technical aspects of electrical design, installation. Quite an avid member of the Institute of Clerk of Work, so quite heavily involved in quality and control and things that are going on in terms of things that happen out there on site, and a lot of that I feed into various areas, forums, committees and the alike. So yeah, and I'm here today to talk specifically around the armoured and separate conductor things that we're going to be looking at today. So hopefully it's all set to be quite an interesting event.
Brilliant, thank you, Spencer. And hopefully my mic's still working. So one of the questions that we've been asked in the ECA, it's a common one on our helpline, is around design of SWA, the effectiveness of the SWA, protection, earthing, the armouring, and CPCs. And a lot of people sort of question, you know, why are my cables so big when I run it through software? Is there anything I'm missing? Does this sound right? So we thought we'd put this little presentation together to sort of show you where that actually comes from. So in the UK, SWA is heavily used, probably more so than Europe and the rest of the world. We are a nation who just absolutely love armoured, and that's why what we're going to talk about today is only really in effect in the UK, in one of the UK standards. So it's heavily used. It's not used so much out in sort of Europe. Because of this, in 2007, the ECA commissioned the ERA to produce a study on a couple of things. It's all to do with SWA cable. And one of it was basically looking at the effectiveness of the armouring round SWAs. So that's where one of the tables came from many years ago, you know, the equivalent copper of that steel round there. And effectively the ERA sort of concluded when you would sort of run out of room in your armouring as a CPC. And with that, they went one stage further. They used a separate CPC as well, which is quite common practice in the UK, to run your armouring and a separate CPC, either as an earthing conductor or a bonding conductor or both. And despite common belief, where you would think as a designer or installer that running an extra CPC alongside your armour would probably decrease the impedance. It had the other effect. There was a reactance between the two. So the ERA produced a report, and in that report was an appendix 16. We're going to show that with you now. So hopefully on the screen, I'm looking for a little nod from Spencer, hopefully here, that you'll see. Yeah. So from the ERA report in 2007, they found that running a separate CPC with an armoured, actually there was a reactance between the two, and they did interfere with each other. And they came up with an equation and a set of equations for this. On the back end of that, there's a British standard which is all about designing cables with separate CPC and protective devices. And this equation here that I'm showing you made its way into a UK annex. So when we're asked, does this affect Europe? This is a UK specific annex in a document, and it's in the PD CLC TR, which is technical report 50480. So a few people online have already mentioned about this, and that's the report it came into. So you can get hold of that, and in the back of that is the set of equations, and from that a lot of software providers made our jobs a lot easier. So it showed the effect, and one of those effects was because of a 0.4 multiplying factor, and Spencer will go into that sort of later on. We're going to go into some demos with Spencer and using software like ElectricalOM to help us understand what happens when we do use armoured cables with and without CPCs, and there becomes a saturation effect as well. There's only so far you can go. We're going to look at this sort of with larger cables and smaller cables, and really that's enough from me. We're happy to take questions sort of throughout, so if you've got any questions, put those into the chat. Omar will send them over. If we haven't answered those questions by the end of the session, then we'll answer those at the end. So I'm going to hand over to Spencer now, I hope. Have you got that, Spencer?
Yeah, it's just come through. Just make sure I've set the right screen. There we go. Hopefully you can see.
Yeah, magic.
The software popped up there for ElectricalOM. So I've got some. I've pre-built a number of examples here, which I'm going to go through, looking at the various aspects of running armored cables and the various effects that it has when we run them in different installation types. I've started with some very basic ones, so I've got some really quite small armored cables. So for instance, if I just go into this particular item here, we can go to the circuit editor menu. You can see here I've run a 10mm armored cable. I've given it a particular length in this case, and the reason why I've given it this length is because overall I want it to fail when it's a fault loop impedance. So I've taken a cable, I've sized it correctly in terms of the protective device, the total load that it can take. So my cable's okay in terms of its minimum IC for selecting the IT of our cable. But I've given it a particular length, so the only thing I'm really failing on is the overall fault loop impedance. And the first thing a lot of designers do in this situation is throw copper at it. We're going to throw in an extra earth conductor and those sorts of things. And with the smaller conductors like that, that works quite well. Now, if I go to the earthing conductor here, you can see currently I do have a 42mm squared armor. So this is it in steel. And down here, you can see the overall equivalent value there, where we use the ratio of the K factors to calculate the difference. So we know that this is the 42mm squared is around about 13.51 millimeters, a copper equivalent in terms of that. Overall, my adiabatic's fine as well, so I'm well within my adiabatic. It's just the issue in terms of the overall impedance of that cable is not going to give me my disconnection time from my protective device. So there's a couple of ways I can deal with that. I can either change the protective device if necessary. If I don't actually need my full 32 amps, I could reduce that down. But like I say, in a lot of cases, what will happen is you might throw an extra earthing conductor in there, and there's a couple of ways that we can do that. So the first one, if I go to my example just here, exactly the same layout, so same conductor, same installation method. So I've just done it relatively clip direct. And if I go to the earth in here, what I've done is I've added just a 2.5mm earth conductor to run separately to our armor. Obviously, they're bonded together at either end of the armored cable. But as you can see, it's reduced my earth fault loop impedance just enough to pip me past the point that I'm going to get my disconnection time under a fault condition for that device. Now we've got some other details in here that are showing up, which I'm going to talk a little bit about later on. For now, I just want to focus on what is happening with the earth fault loop impedances in these different circumstances, and we'll come back to that here. Below that, I've also done two other options that we could have run with this. So I could have just run this as a separate conductor and completely omitted the armor of the cable itself. Obviously, we'd still need to bond at least one end of the armored cable, but I can omit in this case because my cable is a clip direct cable. I'm not required by the regulations in this particular case to use the armor as a protective conductor. But there are circumstances naturally in terms of installation in ground where that absolutely is the case, and we'll touch on that in a little while as well. And then my other option is I could have just changed the type of armor cable I'm using, so it has an integral core of the cable. So naturally another 10mm cable, and in this case it gets me there. So I mean, in terms of this values at the moment, these are roughly going to be there and thereabouts. You can see a slight difference between the two values though, where I've run the copper conductor and I've run the integral conductor. Very negligible at this size, and the reason why it's negligible is because when we look at the ERA, when we're running a copper conductor along with a steel armor or steel conductor of some description, we have to take into account things like EMC and those sorts of things. And this generally comes up as a reactive value within the calculations. So when Darren shared up the calculations here from the ERA document, I'm just going to pop that up on the screen just here. We can see how our overall cable impedance is going to be calculated. So this particular calculation here is for the fault current, but we're only interested really at the moment in this bottom bit. So this is all about calculating the overall impedance. So we've got our resistive elements, we have our reactive elements, and then that calculates together to give us our overall impedance or our Z value, which we can see here in the software. So I've got this value which appears here. I'll just pop a little magnifier over that so you can see where this value is. So you can see that we're calculating various impedance values, including various reactive values in relation to calculations as required. Very little in terms of those at small cable sizes like this, like I say, and that is quite important in terms of some of the stuff we're going to look at following on to this. So here I can see that my Z2, you can see that the overall value here comes to 0.2887. That off there. If we go to my separate conductor option, you will see that that is actually just slightly higher. And the reason for that is when we are looking at this calculation, which comes under the TR 50480, you'll see me looking away because I made little cheat notes for today just to remind me on the little various regulations are going to pop through as we talk through this. But so we can see that there's a slight change there, and the reason and where that comes from is, again, if I pop back to our ERA document, when we're looking at the reactive value and we're looking specifically at armored cables with a steel armor in this case, we need to take into account this calculation here, and this 0.4 value becomes very, very important in terms of that reactive element there. So you can see here we're doing this by 0.4. we times it by the length of our conductor, which is in place, and then we divide it by 1,000, obviously, because we're talking our millimeter ohms per meter as we're going through there. So reduce that down, and that forms part of this calculation for our reactive element up here, adding to our resistive components using the calculation. You can just about see actually the square roots there. This document's a little bit bad on the, on the formatting there, but the square roots for each of the components, adding those sections together, so we can get our overall. Now, when we've done that, that's given us this value here, and because I'm using this with a separate conductor, it does increase the overall value going through that. Now, just to show that this will reduce when we're not using the armor. So if I just pop this on, you can see how there's my changes here, but also if I just turn off entirely. So for instance, if I go to my separate conductor here where I've got the full armored, you'll see the biggest effect. So currently at the moment, I've got 0.4022 in terms of my overall Z2, my earth resistance, or my earth impedance, sorry, overall earth impedance for this particular type of circuit. If I turn off this particular calculation, the software, because this is an option we provide in the software, because the software is used internationally as well as domestically. We're here within the UK. This is something that is very specific to the UK. It's a national annex, as Darren explained, which is specific to UK requirements. So now I'm just going to go in. I'm just going to turn off this option here, and you'll see quite a large change in the number here. So I just turn that off. Now we go through. As you can see, that number now has reduced, because effectively all we're doing now is we are adding up our resistances in parallel as we would standardly do when you're thinking about doing conductors in parallel, so on and so forth. So it does make quite the difference, and that is what's making our difference overall here when we look at our earth fault loop impedance later on, and it's this earthing element which becomes the questionable area when we're trying to do this. So hopefully so far everyone's following me along quite happily with all of that. I'm assuming there's been no questions so far. Darren, pop up in the...
No questions so far has popped up, but we always welcome, like I say, at the moment we're showing you the negligible effect, you know, when it comes to small armors. But
yeah, now this is small armors, I'd say, yeah. Well, sorry, I think the sound's a bit off. I think I'm hearing you slightly later than you're talking. Sorry if I was talking over you a bit there. Like you say, the effects here are negligible because we're working with small cables. So our overall resistances and impedances are going to be quite high in terms of the overall effects for the cables. When we get to much larger cables, our impedances become much smaller overall, because we've got large diameter cables, better resistive load, so we can take more current and those sorts of things. But then this 0.4 value becomes a lot more intrusive into what we're trying to design, because effectively at a point, your 0.4 value becomes higher than the overall impedance that you have for your earthing conductors. And I'll show you the example of that here. So the first one here, again, I've got just a standard armored cable. In this case, though, I've gone for 8 240 mils in parallel. I've put it in the ground as well, but I've got a protected device in place. I've selected a manufacturer here for the earth fault loop impedance values. The manufacturer is obviously available. But here we have the overall values in relation then to our earthing, so we can see the cross-sectional area. And overall, my earthing comes to around about, just for the armor alone, my sets here, 0.02 of an ohm, just nearly 0.03. So I'll just zoom in on that one again there, so we can see where that relevant information is there. Now, when I then move over, and again, I've got the second example set up as I did before, except this time I've done it with an external CPC. Now, because we've done it with the external CPC, we have to use the calculation as we see here, where we're adding in this reactive value into our cable. And overall now, this reactive value is higher than the actual cables themselves. So what you see here on RZ2 is you see that the value has actually increased considerably. So before we were down to 0.0 of an ohm, and now we're up to 0.1 of an ohm at least, which is a huge value in terms of things like our earth fault loop impedance, as we see here. And if I switch between these two, you can see that. So we've gone from having an earth fault loop impedance of 0.03 to then it jumping all the way up to 0.138. And that's as a result of this. So when it comes to where you have to use your armor, and the reason why I've chosen the in-ground option here is because in BS 7671, we've got regulation 522.8.10, which requires that any cable directly buried in the ground, the armor itself must be suitable as a protective conductor. Yeah. So we place this in here. Like I say, on this first one, I've got it just in, but it only just fails. And you would think just throwing in an extra couple of armors there, or an extra few earths in there, would then bring that down. But unfortunately, because of the way this calculation works from the annex of the technical document we were looking at there, it actually ends up increasing it. So that's the first sort of hurdle you go over there. Now, there are other ways to get around this. Generally, this is a big problem with multi-core armored cables. Generally, if you go for things like single core armored cables, you can have an aluminium armor. When we're looking at things with aluminium armors and those sorts of things, they're not required to undergo this check part of it, because it's all about the EMC, the magnetic effects of the armor. So because we don't have that with an aluminium conductor, we can quite happily throw additional cables in parallel and get that affected or the expected effect when we do parallel those conductors up there. So that's it so far in a nutshell. The next thing though I want to take a look at is that something else within the ECA, the document that's here on the ECA, but also appears in the TR document from which is available from BSI. If I scroll down here, we can see some further equations that come in here. And these equations are for when we are using this specific sort of layout where we have our armored cable with our separate conductor. You'll see down here that in this particular type of circumstance, we've added a section which says further adiabatic checks. Now, this is new in the software. So what you're seeing here is pretty much only my version that I have here at the moment. This isn't sort of out there in the standard version. If there's anybody in the background watching the webinar playing around with the software, we're going through this. But this takes into account these calculations as we see here. And what it does is it allows us to split down what the proportion of fault current is going to be passing individually through the armor and the earth conductor under a fault condition. Now, the other thing I want to point out from here is because the way these calculations are made up and the fact that this is that the calculations are created based upon tests and things that have been done under specific conditions, it doesn't add in the same way we would expect it to simply add mathematically if we were doing this based upon a theoretical mathematical system of checks. So what you will tend to find, and if I pop up the little information marker here, is we have put in some information around where these calculations come from. So you can see the information relevant to the TR document. You can see which specific calculations from the national annex that we're referring to. But this second paragraph is quite important in terms of what the values we'll see here are going to be. And that's the sum of those calculated currents, which we have here. So for our earth fault, we have 1.5844. These numbers may not add directly up to the specific value here, can be higher than what you see there, because these are based upon the tested values there, and it's mainly to do with things to do with phase angle and those sorts of things. And you know, we haven't in the calculations are provided in the document, they haven't recorded the difference in the phase angles for power factors and those sorts of things in relation to that. So just want to bring that and show that as information in there as well. So here we can see that we split down the CPC and the armor, so we can see individually what they should be adiabatically sized to for the amount of fault current expected to be passing through each of those conductors. Now I have pulled up one more example here, and this is an example where pretty much everything here passes. So I've got my protected device in place, so I've gone for a BS88 this time. I've got my protective device in there, and as you can see from the calculations that are happening here, I'm good on my earth fault loop impedance. So I've got my disconnection time. I have cut it close to the bone, as you'll see here. So overall, I do have up to 5 seconds available here, but I've cut it right up to 4.98, and I've done that quite intentionally for this example. So I can get the sort of the pass fail information. Again, this is just clip direct, so you know we're just out of the ground, and we can see obviously in our phase faults we've got our short circuit faults, so we've got disconnection on the device and short circuit. If we go to the earthing, you'll even see that my adiabatic overall for my armor and separate conductor are also passing absolutely fine. However, when we look at the adiabatic check for the individual conductor being used for our separate, we can see that it fails in terms of its operation under fault. And to show this a little bit more, we've gone even further, and we've actually plotted this into our selectivity study. So if I go to the selectivity study tab here, I can see my general fault currents. And for now, I am just going to turn off my phase fault information. So we're just going to focus on purely the earth fault in here. And at the moment, I've got 3 earth fault lines here. My first brown one here is my overall fault current, which is related to what we see just down here in terms of our disconnection time for our overall conductors there in parallel. We also have 2 slightly different ones. So we've got the fault current that's passing through our armor, which is this slightly darker color here, and then we've got the earth fault current that's passing specifically through our separate conductor. And if we go down here, this is all keyed up, and if I then place on my adiabatic lines, so I've just set my adiabatic lines for my earth conductors here. You can see here's my adiabatic line for my armor plus my separate conductor. Here's the adiabatic line purely for the armor on its own, and here is the adiabatic line for the individual CPC that we've placed there. I'm also going to place on here the disconnection time of our device here. So across the line here, we can see that our device is going to disconnect in 0.48 seconds, and we can see that from where it intersects with our overall earth fault level here against our fuse. However, if we go to our separate conductor just here, we can see that the fault line intersects with the adiabatic line of our separate conductor before our disconnection time on our device. So even though this overall complies in terms of the overall adiabatic check of the conductors in parallel, separately, with the amount of fault currents that are expected to pass through each one, there's a possibility that the separate conductor could be damaged or destroyed in the event of a fault there. And that is the other part here which we are looking at in terms of these calculations which appear within the TR document. And you can see here it's quite specifically saying where the above equations are used, it is necessary to calculate the proportion of fault current carried by the external CPC to determine whether the fault current withstand of the external CPC is adequate. And in this particular case, we've proved that it's not. So that's something else that we're showing in the software. Now, before this was sort of automated in the background, you weren't really seeing it or why it was, but there was a problem with those sorts of things. So what we've done in what's coming up, and obviously the current versions coming, is you're actually going to fully see this. You're going to be able to see it on the adiabatic. You're going to be able to see it in your selectivity study. So it just makes the information a bit more overall clear and useful. With that, I think I've covered pretty much everything in relation, hopefully, to this subject. So hopefully I've explained it well enough for people. I would really like to open the floor to questions.
Hi there both, just Omar here. Darren, I've just forwarded a question through to you. Let me know if you can't see it.
Lost your audio, Darren.
Just get my webcam up on there. So Darren, we
No,
can't hear you.
I can see you moving, your mouth's moving.
Is that any better?
Yep.
Ah, there we go. Yeah.
Right, audio's back. Let me know if it drops out again. No, I can't see any questions yet, Omar, on the software.
So I'll just read this out. Yeah. I've got an echo from someone, not sure who it is. So if you could go on mute, please, that'd be great. Question is, why is reactance an issue? Is it an issue in fault conditions or in normal working conditions?
This is specifically the tests that were done, I believe, under fault conditions for the ERA. So they were looking at what happens under fault, you know, where the fault currents are going and how those are dividing out, obviously, naturally between the separate conductors and if there were any potential things there. So, like I say, this is done under tests. So what we refer to as empirical calculations has been done based upon tests in a lab, effectively. And then the equations have then been derived from the test results of that. So the equations match the overall testing methodology of what's happened there, rather than just sort of the theoretical calculations. So it does behave differently, which you'll often find with empirical results.
Thank you, Spencer. Just for the audience there, I've shared a link to that BSI document that Darren mentioned. That's in the chat now. You should be able to access that. We'll have a few links for follow-up that'll be available in follow-up email for attendees on this webinar, and also in the description of the video once we've got the replay up on our YouTube channel. A couple more questions. So what I'll do, Darren, just now, we'll test this again. I'm going to assign question to Darren Crannis. Let's see if that comes through to you. If not, no worries, I can read them out. Let me see actually if I can copy and paste, send those directly to you, Darren.
Yeah, I can see it. It doesn't come quite through. I can see them now. I can't quite see it in the software.
No worries. It's you're much more qualified than me, obviously. I'm not a technical person, so I'll kind of retreat back into the background and let you take those questions, Darren.
Oh, I can see them now. So yeah, so that one, the reactance one's done. This one, Spencer. Yeah, so when using, oh, they're all coming through. When using a separate conductor with an SWA, are there any other parameters or conditions which would make the impedance value of the conductor worse?
Generally, when it's smaller conductors, you're generally okay. So usually up to around about 400 millimeters. If you throw in a separate conductor about the quarter of the size of your phase conductor, you're going to be okay. It's when you get in to much larger installations where you're trying to supply much larger power. So like maybe you're trying to supply like 900 amps plus to another location, and particularly in ground where you have to use the armor as a protective conductor, because if you're doing it above ground, you're going on spray work and the like, you don't have to use the armor as a protective conductor. You can omit it, but you can obviously naturally bond one end of that, and you know, for the effects on the EMC anyway. So generally it will always be when you're running a separate conductor, your armor and the armor as a steel, it's the only time when it really becomes a particular issue in terms of the calculations, and it has completely the opposite effect to what you would naturally expect when you throw a load of copper at something in parallel.
I think that's
completely the opposite, inverse effect. Yeah,
I think that's the point. There's a lot of people throw more CPC at this. They throw more copper. They keep increasing it in the software, and they don't see that change, and they're still not meeting disconnection times. It's throwing errors. Where what we're saying today actually is there's a saturation point, and there's a point where just throwing more copper at it doesn't work. You have to throw more steel.
And effectively, a saturation point is this calculation here. Yeah, because effectively, once your impedance of your cables is lower than the overall calculated output of this particular part of the equation, that's when it starts flipping on its head and going the other way. Yeah. You've heard me call it like this. I effectively call this a Gandalf number, where it's that you shall not pass. Yeah. And that's effectively what that is doing in that case. So on lower conductors where you have impedances that are genuinely higher than what this value will be, you're going to be fine. It's when you get really low impedance, so large cables, even short distances are usually more of a problem, because naturally those will have lower impedances as well. Also, it plays into a little bit how much fault current you have on your system, but that generally is more to do with the equations down here where we're looking at the fault levels dividing between your different conductors, which is what causes this generally causes this in terms of this issue here. So generally, if you've got much higher fault currents, this actually doesn't really become much of an issue later on down the line anyway. But it's those sorts of things that you need to keep an eye on. Hopefully I answered the question. I haven't gone off piece. I have a tendency of waffling, so tell me shut up.
Ask another. Well, we've got another question, and we did answer this through. It was the effects. What happens when we're using aluminium conductors? Was it SWA cables or aluminium conductors as opposed to copper? So not AWAs with aluminium conductors.
So aluminium conductors, if you're still using a steel armor, I don't think you get really aluminium conductor steel armors. I don't think it's very common if you do. But generally speaking, as long as your material that you're using as your parallel earth is non-ferrous, it's not an issue. It's where we've got these electromagnetic effects. I mean, you can see it partially in the calculations here. So where you look at this and you see this 1.1 value on the armor. So this RA is the resistance of the armor, and the 1.1 is there because this is the considered electromagnetic effect in terms of how that should affect the resistance of the armor. That's why you don't see it with the RCPC here, because it's a copper conductor, it's non-ferrous. With things like, for instance, trunking, the value's 2.1. With conductors that go through a conduit, those sorts of things, I think it's 2.1 for those conductors. It's different, I think, actually, for I can't remember the number off the top of my head, but you see sort of the thing. It's where we're looking at steel ferrous enclosures, and we've got steel ferrous elements in there. When we're using non-ferrous materials like aluminium, it's not consideration, because non-ferrous, the electromagnetic effects are minimum. Not enough for us to concern about.
Actually, we'll probably jump around the questions here. So we've got sort of one says about, you know, cables in containment. Well, if all the cables, like using a 5-core cable, are within the steel containment environment, you're not going to have those problems. But another one we got here is if it's an issue, obviously the SWA with the armouring, what happens if we put this on ladder rack or tray? Does that tray cause a similar magnetic effect?
The tray's not there for as a protective conductor. We're not using it for a protective conductor in that particular case. Generally, it will be bonded at one end or somewhere naturally for your touch voltages and the alike there. But voltages, old school. But yeah.
Well, so generally, it's always bonded for EMC purposes for the technical report and for the ERA study. Again, these are technical studies. That wasn't the facts about within
that. And bear in mind, it is more about when we're using these steels as protective conductors. That's the defining characteristic. If your steel's being used as a protective conductor and you're running it with other conductors that are copper in relation to that protective conductor. So I think it's it's just down here. 543.2.1. Yeah, a protecting conductor may consist of one or more of the following, and it gives you lists there of separate CPCs. It gives you a list of conductors in a cable. It gives you it specifically says a metal covering which covers, and it does have in brackets there, it says things like sheath of the armor and those sorts of things. So your protective conductor can make up as a combination of those. It doesn't specifically specify that it has to be one or the other. But when you are making that up as a multitude, the fact that you've got two different materials there, that's our consideration. And the primary place where we get this is in terms of the armor. The armor is probably the most onerous of these. There are various calculations related to things like when you're using payment, such as a steel conduit or a steel trunk or something along those, but the overall effects aren't as nearly as intensive as when we're using armors, because the armors will tend to use a much bigger sizes, whereas in a containment you'll be using lots of small high impedance cables rather than that. So the effects that you see are so minimal, it's hardly noticeable.
I think that leads on to and I'm going to jump around the question. We said that we tend to run armors inside, on ladder, on tray, all day long. No, we don't have to use the armouring as a CPC, but the only time we do is when we bury it in the ground. That's a definite yes, because we're using that for mechanical protection. It's an exposed conductive part, so we have to do that. And we've got a question in about 522.8.10 is when you put these in
the
ducts.
only exception, sorry. The only exception is if you do it in a duct, So,
so
if you do it in a duct. Sorry.
Yes, it's a brilliant question. If we put it into a duct and the duct meets the requirements of BSEN 61386-24, which is a 750 Newton duct, 750 N duct. So it's what we call probably twin wall ducting, rigid duct or something.
More commonly known as twin wall, is the usual site term people use. If you put a twin wall duct in the ground, it's providing equal or adequate mechanical protection as what the armor should be, so you can omit then the armor in those cases.
And that's a very common question we get when it comes to solar farms and perhaps more DC side of things, where this is very common, but you can use it for AC as well. You see, so there's so a lot
often
of
it comes down to cost in terms of the decision. Often it's a cost decision. So is the crown works going to cost much? Is it going to cost more? Because once we get to this point, I'm assuming my screen's still sharing here.
Still sharing. Keep it on there because we've got some more questions coming.
So I mean, in terms of those sorts of things, the cost benefits you need to weigh up is the fact that multiple separate earthing conductors isn't going to help you. However, the effect doesn't, because the the cores of the cable are contained within the steel armor, the reactive effects aren't applied to the phase conductor. So when you're looking at this, one of the more effective ways, or one of the effective ways of doing it, although it is a massive cost increase, is to increase the overall size of the armor, because then you're increasing the size of your phase conductor. And when you increase the size of your phase conductor, overall, you're reducing your overall impedances as an earth path effectively. So you can reduce this number more effectively by increasing the size of your phase conductor rather than trying to throw more copper at it in parallel. But it all comes down to the size, the number of conductors. Is it more cost effective? Is it going to cost you more to get groundwork and duct work down in there and then bury all that in? You know, and then there's also other benefits that you might look at from a health and safety perspective in terms of, you know, once you've put that in the long term, it's more safety conscious if you've got roots already in the ground that cables can be pulled out of and put back in terms of then future maintenance and those sorts of things. So there's a whole range of stuff, probably going a bit off piece here, but there's a whole range of considerations there in terms of how you might decide to tackle the armor issue when it's particularly in ground. But yeah.
Got a question in saying, how would we fix that last issue? I don't know if it's the one I've explained or the one your last example. One. It was the last one, whichever the last one was. How would you fix it? We said, would you increase the CSA of separate CPC?
Are we talking the last one in terms of this one with the separate earth that's failed?
I believe so.
Or are we talking about the multiple 240 core cables? I'll do both.
Go for both.
I don't mind. I mean, in terms of the separate, it's a simple case of just increasing the size of the separate conductor. And if I increase the size of the separate conductor, it allows more fault current to pass through. Just having to upsize that one particular conductor on the cable. So that will now pass quite happy. Don't have to worry about that. In terms of this particular issue with the multi-core cable, if I can, I'm going to change to single cores and use aluminium armoreds, because I can overall use less armored cable because I don't have to take into account the parallel effects. So it's a much easier, quicker fix overall, and I'll probably get away with using less armoreds in parallel as well, because I've increased the number of armoreds in parallel specifically because I'm trying to get so much power from A to B. The other option is with multi-core cables, there are manufacturers that produce a multi-core armored cable with a copper armor. Yeah, again, it is slightly more expensive, but on a 320 meter run like this, I can reduce this probably down to 3 or 4 cables in parallel overall. And putting the armor directly in the ground and burying it is a lot more cost effective than doing the groundwork and putting a load of duct work and everything else in there in relation to that. Plus, because of the number I've got in parallel, I've also got to take into account my correction factors. So for instance, here I've got a correction factor for the grouping of the overall, because these are all going to be cable under simultaneous overload. I've got a grouping factor of 0.5. So I'm halving my cable's effective current carrying capacity and those sorts of things there. So the more I can reduce that, the better. So my two options for this would be either single core aluminium armoreds or a multi-core armored with a copper armor in there. And generally one of those two would usually, for something like this where I'm having to run such a long run as well, would usually end up cheaper than doing a lot of groundwork for either a duct system or a trench or trough system that might need to go in there as well. And not to mention, when you put those in, you need drainage systems, and the groundwork costs can start to escalate quite quickly, depending on the situation and the location in the country as well. Inland not too bad, but you're closer to the coast and you're going to have a lot higher water tables, so you know, drainage and everything, you don't want to blow the armoreds, so you might end up having to put in armoreds with additional waterproof protection in there as a layer within the XLP and everything else as well. So again, I'm running off these, so but yeah, hopefully I haven't information overload, sorry.
They keep coming. So is there simple guidance rules on when to use additional separate earth conductor
Sorry,
ways to
Darren, I'm
avoid
really
it.
struggling to hear you a bit there. You're quite quiet all of a sudden.
It is.
So I'll turn my volume up a bit. There we go. Oh, I've lost you altogether now.
Any better? Okay.
There we go. Yeah.
There we go. Yeah. Is that better?
Yep, all good. We can hear you, Darren.
Okay. So while I'm there, is there any simple rules or simple guidance when you're going to need to use a separate CPC? Is there more of effect when you run, for example, 2 parallel 70s, 2 parallel 1854 cores? Is there any time it's going to be worse on smaller cables than it is on bigger cables?
Generally, only if you're using short runs. But because it's the overall impedance that we're considering. Yeah. So if you've got low impedances of cables and you're running the separate armor with the steel as protective conductors, it's the low impedances that are going to kill you. You gave an example of 70s and 95s. I mean, the effects at those sizes, if you're only looking at relatively small, so parallel to looking 300 amps, something like that for those sorts of cables, 350 amps, the effects are going to be relatively negligible, to be honest. Generally, it comes up when you've got much bigger, you're trying to do large scale site distribution. You will see a change, or you will see a slight effect between the two in terms of the possible upsizing of a phase conductor. But at those sizes, I'd probably rather upsize the phase conductor of my armor than try to put in groundwork and additional earths, which aren't actually going to do the job when you look at the calculators anyway. So yeah, usually the easier option is just to go up an additional size or two on the physical armor itself, or on the physical armored cable for the phase conductors itself, because that will overall reduce your earth fault impedance path.
I think we've got a question about is the answer to, I'd imagine this is maybe during verification or maybe EICRs. Is it to check and an upgrade to the separate CPC to ensure compliance? The thing is unless it's part of the design or you've got the design, you've got to be very careful about just going along and adding a separate CPC, because you could actually have a detrimental effect on that. I don't know what your thoughts are, Spencer.
Yeah, without doing a calculation on it, I wouldn't say do that, because if you do, you could actually be, I mean, and looking at what we're seeing here, you could actually be adding a negative effect to the system rather than helping with the overall effect. In a dead test situation or in a live test situation where your multifunction test meters, it's not going to take into account those. So you're not going to be generating the levels of fault current that are eventually going to end up passing through those conductors, which is where reactive elements come into play there. So yeah, it's a case of performing some form of study and check mathematically using the formulas and the calculations as provided within the documentation in order to ensure whether or not adding that additional armor is going, or sorry, that additional earth to the armor is actually going to be effective.
Okay. Just a clarification. Someone just wants the answer again to using a duct. Can we put armors in ducts, and can we effectively omit, the armor in as a CPC? So this is about a 750N duct, so a twin wall duct offers enough mechanical protection in line with regulation 419.3 that you don't have to use the armoring as a mechanical protection for that cable. So as long as the cable's bonded one end, you don't have that what we call SWA effect. You can ignore the armoring as the CPC. So just to go over sort of that one there. Does BICC data change anything in regards to the calculation when buried direct or with inducting in the ground?
So BICC data and even the So you might refer to BLCC data as one. The other one that's commonly used for cables in ground is the ERA options. There is a separate paper than what we were looking at today, which is in relation to conductors buried in ground, but that's more specifically around the ground conditions, ground temperatures, and how that overall affects the effective current carrying capacity of the cables. It's not really looking at anything to do with changing the physical, impeditive or reactive properties of the conductors. So in this particular case, no.
I think that brings us to just checking through all of our questions. I think it's just worth sort of summing this up really, that it's been a great session today. It's probably one of our longest webinars and actually one of our most interactive webinars. So really looking forward to this going out on catch up. So some people's asked, is this going to be available on catch up? And that's going to be sort of in the next day or two. I'm not going to put any pressure on Omar, he's just returned from leave. So we're going to have that available pretty soon. That'll be on our YouTube channel. Yeah, that'll be on our YouTube. Yeah, so that's youtube.com/ECA Live. There are lots of these on our YouTube channel. It's a very underused channel, shall we say, by everyone. So if you're on the webinar today, have a look there. We've got lots of learning zones on there, some technical Tuesdays and lots of other videos as well. So to summary really up today, yes, we all use SWA and the Armoured and CPC. You can do that all the time. When you do run an additional CPC, it has an effect, and it has an effect on the overall earth fault loop impedance, and it may affect the protective device. This is highlighted in 2007 when the ECA commissioned the ERA to produce a report. That went into a technical report with a UK annex, and we put a link to that in the webinar, and we'll probably put a link to that in any notes that accompany this as well to show that is available, and it's a UK annex, and software providers take that on board. You can get access to that technical report, obviously the link we're going to put in. It's also in the IET design guide. This really is where software has its benefits, because doing this longhand, especially with this UK annex, can be quite tiresome. And practical ways to overcome this, you're looking at increasing your armor in size, you're looking at parallels, you're looking at burying cables in ducts which meet the requirements, and single point bonding for sort of aluminium wire arms and other things like that. So we have no more questions. It's been a great session, so I'm going to hand back to Omar.
Thank you, Darren, and thank you, Spencer, for that really great presentation. Like I said at the beginning, trying to make this a bit more interactive for our members, for our audience. So thank you very much for taking part. Had a really active Q&A section this webinar. Hopefully you've all gained something from this. As mentioned, this has been recorded, and the replay will be on the ECA YouTube channel. We're also in the process of bringing all the past webinar recordings onto the ECA website, so they'll be accessible directly there for members in the members area of the website. We've mentioned a few resources today. There's a link to the BSI document that Darren mentioned in the chat here today. What I'll do before uploading the replay is gather up all those links to all those resources we've mentioned, and I'll kind of collate them, have them all in one place, either in the description on this video on YouTube down below, or on the ECA website, easily accessible. So that's it, we'll wrap up there. Thank you very much once again to everyone for joining us this afternoon, and have a great rest of your day.
Thank you, everyone.
Thank you all.